Okay, so yeah, we did pass paper questions, and we had just talked about, I mean, this was how far we had done. We had just introduced orbitals. So let me start over here. SP and d orbitals, and f orbitals had, I told you, it had 7 lobes. It had 6 to 8 lobes. So the negative charge of the electron around the nucleus can be distributed in many different ways. So it could either be S, P, or D. And so I'm going to talk about subshells now. So this is where we had to start. So I'm going to talk about subshells. Now, subshells, I mean, it's already discussed. It's a group of degenerate or same type of orbitals. So group of degenerate is the word. I mean, they use all of this fancy terminology. It just means same type. A group of degenerate or same type, same energy level of orbitals. So for example, you've got this p orbital. And remember, each orbital can have a maximum of 2 electrons. And so there's a bunch of electrons with the negative charge distributed on the x-axis. There might be another p orbital, and the negative charge of the electron could be distributed on the y-axis. So that's another type of p orbital. We can change 1 second. So that's another type of p orbital. Or we can have the negative charge of the electron. It could be distributed on the z-axis. So that's another thing that can happen. So the negative charge of the electron is distributed on the z-axis. So the thing is that if you combine all those 3 orbitals together, that's known as a p subshell. So that's a p subshell. And the same goes for the d subshell as well. So if you combine all the same type of orbitals together, that would be referred to as a subshell. That's it. So there's no science to it. It's basically just orbitals. You're just grouping them together. That's it. So if you have many different types of d orbitals, you can kind of group them together, and that would be known as, I mean, like if I copy this, there would be many different orientations of this. So either, like if we copy this, so that's a p subshell. I mean, drawing the D is slightly more complicated. So either the negative charge of the electron is, now D has 4 lobes. So either the negative charge of the electron is spread on the X and Y axis, or if you have another one, maybe the negative charge of the electron or some other electron is located between the X and Y axis. So you can imagine many different types of arrangements of the D as shown over here. I mean, none of them are overlapping. All the negative charge are located in different places. They're all located in different planes. So the thing is that a subshell is a group of degenerate orbitals, and you should know which of those orbitals combine to form which subshells. So starting with the first one, you've got the S subshell. That's the first one. It only has one s orbital. That's it, because it doesn't have any different types. I mean, there's only one type of s orbital, and you can have a maximum of 2 electrons. Then you have a p subshell. There are 3 different types of p orbitals. So you can have px, py, and you can have a pz orbital. And that can have a maximum of 6 electrons, because each one of the orbitals, like each one of the spaces over here, can accommodate a maximum of 2 electrons. So there could be 2 electrons in this black area, 2 in the green, 2 in the red area. Similarly, you're going to have a d subshell, and that will have a maximum of 5 different orbitals. These are just the names of the orbitals. They don't, I mean, this x squared minus y squared makes no sense whatsoever. It's just a name. It's just a name that's given to it based on its symmetry. So just remember that, I mean, for example, px, py, pz, that just indicates that the electron and the negative charge of the electron is on the x, y, and z axis. So D can have a maximum of 10 electrons. And the last one is your F subshell, which hardly exists in any atom, so that's not really important. Just remember there are 7 different types of F orbitals, and maximum electrons that can be accommodated in an F are 14. So subshells is just a different way of thinking of orbitals and grouping the same type of orbitals together. Now, at the moment, we haven't studied how the electrons are going to fit into those orbitals. We're just talking about how, like, what are the possible ways in which the electron could exist around the nucleus. The next thing is, and we're going to jump to this now. So the question is, I've got a bunch of orbitals. I've got a bunch of, like, there's lots of spaces where the negative charge of the electron could be located. There are S, P, and D areas. And so how do I figure out where the electron is? So we're going to jump to writing electronic configurations, and we're going to fill in the details after that. So remember that each orbital, if I haven't written this, I'm going to add this, that each orbital can have a maximum of 2 electrons. Has maximum of 2 electrons. Now, how do you figure out where the electrons are? Whether they are in the S or the P or the D, like, how do you figure that out? For that, you have a table which is known as the Aufbau principle that helps you in figuring this out. The Aufbau principle is it's just a simple table which would be used to write electronic configurations. So it's a table which is, you've got 1s, and then you've got, you can write 2s, and 3s, and 4s. And it just continues. You can just keep going downwards. This starts with 2p, then you have 3p, then you have 4p, then you have 3d, and 4d, and then you have 4f. So your f starts at this point, and you can just continue this downwards. It's going to be 5s, 5p, 5d, and so on. So you can just keep filling the table, but you don't need, I mean, most atoms are small. Most of the common atoms are small. Like most of the everyday atoms that you talk about, they're very, very tiny. Now, what does the Aufbau principle mean? What it means is, first thing, the notation. We're going to talk about the notation. Like, you see 2p over here, and you've got 3p. And similarly, there's 4p written as well. What does it all mean? That's the first thing. What is this 2 or 3 or 4? That's known as the principal quantum number. So that's your principal quantum number, which is also known as the shell number. So different orbitals or subshells will have this 2 or 3 or 4 or 1 in this case. Like over here, there's 1 written as well. So these would be written. So what is a shell? I mean, what is it? I mean, what does this thing represent? What's a principal quantum number? So remember this, a shell is not a physical thing. Shell represents, or principal quantum number represents, energy level. It represents how energetic the electron is. That is what it represents. So if you have a more energetic electron, or a bigger number, or what we can write as a bigger number represents a more energetic subshell. And basically it's the energy of the electron. So bigger number represents higher energy. TK, is this clear?
Yes. Yes.
Now, so bigger number represents higher energy. Now the thing is, how can you relate energy to what we just studied? I told you that electrons are going to be located. So electrons are going to be located. Just one second. Sorry. So we talked about orbitals and grouping orbitals together into subshells. What we're going to talk about is how can we relate that to energy levels? Like what are these numbers? So what they represent is, like you can see over here in the table over here, that where I listed all the orbitals and subshells, there's 1s, 2s, 3s. So what does that mean? So let's say I have 1s, I've got 2s, and I've got 3s. So if there are electrons in the 1s and there are electrons in the 2s and there are electrons in the 3s, how are those electrons different? 1s means low energy, because the smaller the number, the lower the energy. And 3s represents a higher energy. That just means that the electron is it represents the electron is very energetic. And as the numbers continue to increase, the energy levels would increase. So if the electron is in the 1s, that means the electron is going to be occupying a spherical region. The negative charge of the electron is going to be spread out in a spherical region around the nucleus. So there's going to be negative charge in this spherical region. So, but the thing is that the electron would be very close to the nucleus, because the electron is getting attracted by the nucleus. And the electron has very low energy. So the electron would be sticking very close to the nucleus. It can't really fly away very far away because it doesn't have a lot of energy. On the other hand, if the same electron is existing in the 3s subshell or orbital, then that means that the electron would be occupying a much bigger space, because the electron would be more energetic, and that particular electron would be more energetic, and it would be flying around, buzzing around, just like a bee. It would be buzzing around and occupying much bigger areas. It can overcome the force of attraction of the nucleus. Like the nucleus is in the center, so it can overcome the attraction of the nucleus and fly away much further away. So that is what difference these numbers would make. These numbers, these shell numbers, these principal quantum numbers, they represent the energy of the electron. So the subshell remains, I mean, the shape of the subshell, the shape of the orbital, that remains exactly the same, except that the amount of space that they're occupying, that increases. The electron is now much further away. Is this clear to everyone?
Yes.
Yes.
So you've got, so this is how this would change. So remember, it's not a shell number, or shell is not a physical thing. Now, one thing that you should know is the bigger the shell number, the further the electron is away from the nucleus, the less attracted it's going to be. So electrons are always going to be lost from higher energy shells or bigger shells first because they're further away. The electrons that are close to the nucleus, they're going to be very tightly held or attracted by the nucleus. Now coming back to the Aufbau principle. So that means this one, two, I mean, you've got subshells and they have different energy levels. And remember, it's a table of subshells. I mean, this thing that I've drawn, that's a table of different subshells that you have. I mean, for example, this P over here represents 3 orbitals, Px, Py, and Pz. Now to write electronic configurations, what you'll do is you'll draw diagonal arrows. And so you'll draw the diagonal arrows and you start following the arrows from the top. Just like in your O levels, you studied that it's 2, 8, 8. You start from the top and you just start following the arrows. So for example, if I start writing electronic configurations of different atoms, I just need to follow the arrows, and for every atom, it's kind of going to be exactly the same. There would be some exceptions because not all atoms, they follow the Aufbau principle exactly, but most atoms, they do follow the Aufbau principle. They do follow this table. So let's start with neon. That's 8 electrons. So let's try and figure out the electronic configuration of neon. That's starting with the first arrow. You've got electrons in the 1s. So remember this 1, I mean, this 2, etc. It's not quantity, it's just the energy level. So let's start with 1s. There's going to be maximum 2 electrons in the 1s. After 1s, you follow the other arrow, the second arrow, that's 2s. The electrons are always going to be written at the top by a small subscript. Then you have 2s. That is going to have a maximum of 2 electrons as well, because the S has a maximum of 2 electrons. Okay, remember, this 2 doesn't mean that you have 2 different s orbitals. It just means 2 over here is the energy level. It doesn't, I mean, it's still the same s orbital, but a higher energy s orbital with 2 electrons. And after 2s, you have 2p. And let me just correct it. Neon actually has 10 electrons, not 8. So now 2p subshell can have a maximum of 6 electrons. That's what we studied over here. That the p subshell can have a maximum of 6 electrons because there are 3 different types of p orbitals. So that's how neon would look like. And I'm going to draw or sketch how neon's electrons are going to behave. Like, what does this all mean? So the first one, 1s2, it just means that 2 of the electrons, like this one, I mean, 1s2 means that there are 2 electrons in a spherically shaped region. So those 2 electrons would be very close to the nucleus, and there are going to be 2 electrons that would be buzzing in this area very, very close to the nucleus. Then you've got a 2s subshell with 2 electrons in it. Now the 2s subshell is a higher energy subshell. That just means that the electrons this time are like slightly further away. I mean, they're still occupying a spherical region around the nucleus, but these 2 electrons are buzzing or existing in areas much further away from the nucleus. The electrons can kind of overlap, but these 2 electrons, their energy levels, the electrons are just existing. The negative charge is spread around areas very close to the nucleus in a spherical region. 2s over here represents the electrons being spread out over a much bigger area and still in a spherically shaped orbital. Then you have the 2p6. Now the 2p subshell has 3 different orbitals. So that means the electron could be on the x-axis, it could be on the y-axis, or it could be on the z-axis. So I've just drawn 3 axes, and let's call this the x, this one as the y, and this one as the z. So 2p6 means that they're all occupied fully. So if I start drawing those, that means there are 2 electrons in the 2px area. So there are 2 electrons that are buzzing in this, on this axis. The negative charge is spread out over these areas. You've got 2 electrons in the 2py, and there are 2 electrons that are located in the 2pz. So there are 2 electrons that are buzzing around in this area. Just a second. So that's how a neon atom would actually look like. It's 10 electrons are going to behave in this way. 2 electrons very close to the nucleus, negative charge, all spread, they're low energy. 2s means, you got 2 electrons, and those 2 electrons would be occupying, or negative charge, they would be spread around a much bigger area, but it's going to be a spherical region. And then you have the 2p6. So the electrons would be in this way. 2 electrons, negative charge, spread in this area, 2 electrons, 2 electrons. Is this clear?
Yes.
Sir, could you show the 2s2?
Yes.
Which one?
The 2s2. Where is that on the diagram?
The 2s2 is the green one. No, it's this one.
And the 1s2 is also the green one. Oh, or is the red one?
It's the red one. Well, the 1s is the lower energy, so it's the electron is
Yeah.
much closer to the nucleus, right? The 2s is the higher energy one, so the electron is slightly further away. So the negative charge is distributed in a much bigger area. And the 2p6, there would be 3 different axes on which the 6 electrons would exist. Is that clear?
Yes. Sir.
Yeah.
In our exam, will we need to know how to draw this diagram? Like we have to draw something like that?
That's not important, but the knowledge about, because you can't draw them, they can't expect, I mean, especially when the drawing is complicated, they can't expect you to draw these diagrams, right? So they wouldn't ask you to draw these diagrams, but they might ask you, like if this is the electronic configuration, they might ask you to draw 2s2 or draw 1s2 and 2s2 on separate diagrams. I mean, you get a lot of questions.
Oh,
like,
I see.
so they might ask you to draw 2px or 2p. I mean, they would ask you to draw individual ones, not the whole atom, because it's too complicated. You can't, I mean, they can't expect you to actually, I mean, no one is good with drawing. So they probably won't, they would never actually ask you for this. But the individual ones, they will.
All right.
So you can write electronic configurations of many different atoms using this. So let's do iron, which is 26 electrons. Now, iron having 26 electrons means if I draw iron, let me just. So Fe would be, you start following the arrows. It's going to be 1s2. Then it's going to be 2s2. The third arrow is 2p6. I mean, the third arrow, it's 2p6, 3s2. So that's the third arrow. Followed by the fourth arrow, which is 3p6 and 4s2. And after that, how many electrons is this? This is like 20? 18, just a second. I think this is 20 electrons up till 4s2. So you need 6 electrons. So the 3D over here can accommodate a maximum of 10 electrons, because remember the 3D subshell has 5 different types of d orbitals, so it can have a maximum of 10 electrons. So the 3D over here can have a maximum of I mean, you're just left with, you've run out of electrons. So it's going to have just 6 electrons. So that's 26. Otherwise, it can have a maximum of 10 electrons. So that's the electronic configuration of an iron atom. Is that clear?
Yes.
Yes.
So one thing that you should do is that this table over here, it's not ordered properly. Like when you write electronic configurations, the order is not. I mean, it's not always the right order. So one thing, once you use the OFF principle, make sure that the order is correct. I mean, it wouldn't really matter. I mean, it's not that matter. It doesn't matter that much, but conventionally speaking, the order should be correct. Like over here, the first shell, then you should have the second shell, then you should have the third shell, and then you should have the fourth shell. So one thing that it's recommended that you should do is correct the orders. Like get the 4s2 on the outside and the 3d6. I mean, we didn't change the electronic configuration. I just reordered them. Group the third shell electrons together. Group the second shell electrons together. The fourth shell electrons. So it's better to actually arrange them properly and neatly. The table is not always going to do that for you. The reason it's important is because when you remove electrons, electrons are always removed from the furthest subshell first. Like the electrons which are really on the outside, they're going to be removed first. So which is why it's important that you order them properly. Don't change the electronic configuration, write the electronic configuration, just rearrange, group them together. Is that clear?
Yep.
Yes.
So using this, you can write pretty much any electronic configuration. Now, a few minor things when you're writing electronic configurations, especially for atoms like these. So the question is, there are two questions that need to be answered. One is, how do 2 electrons exist? Like we said that an orbital will have a maximum of 2 electrons. So the question is, how do 2 electrons exist in the same orbital? That's one question that's got to be answered. So like you have an s orbital and the 2 electrons that are buzzing around in that. The negative charge of the 2 electrons is spread in this spherical region. Now the negative charge of 1 electron is going to repel the negative charge of the other electron. So it's very hard for 2 electrons to actually exist in the same space. They would try to repel each other. So electrons repel other electrons. And that's known as an electrostatic force of repulsion. So it's pretty hard for the electrons to actually exist in the same orbital because of the negative charge. So how do they actually make that possible? How do 2 electrons, they exist in the same space? The way they do that is that that every electron has a magnetic field associated with it. So every electron has a magnetic field, and electrons, they act as tiny magnets. Like all elementary particles, they have a certain magnetic field associated with them. You've never actually studied this, but this is where magnetism comes in. I mean, you've got magnetic materials. The reason materials are magnetic is that your elementary particles are magnetic. We've always studied about electrons having negative charge, but the thing is that electrons not just, I mean, that's not the only thing that they have. They also have a magnetic field. Think of them as tiny bar magnets. Like you see those bar magnets, right? Like if I So think of them or imagine them as being these tiny bar magnets, which have a certain magnetic field. I mean, so they would emit a magnetic field around them. I mean, just like this. So if there's an electron that's buzzing around, that electron would kind of have, this one electron would have a magnetic field. This other electron would also have a north pole and a south pole, and it's going to have a magnetic field that's surrounding it. Is that part clear?
Yes.
Now the thing is
Yeah.
I said, remember, in the universe you have three major forces, right? You've got gravitational force, which is always an attractive force. You've got an electrostatic force, which can be both. It could be a repulsive force, it could be an attractive force, depending on positive and negative, right? In this case, both electrons are negatively charged, so that means they would always repel each other. I mean, it's impossible for them to electrostatically attract each other, because an electron would always be negative, the other electron would always be negative, so they're always going to repel each other. And the same applies to magnetic fields. Magnetic fields, if something has a magnetic field, then magnetism, it can attract, it can repel, and it will attract if the dipoles, this is known as a dipole. Dipole means two poles, like you've got a north pole and you've got a south pole. So imagine an electron, a tiny electron. There would be magnetic field lines going out of it and coming into it. So it will have a dipole. It will have a di means two. So it will have two poles, north and south. So if one electron and the other electron has an opposite magnetic field, like if this one has south, the other one has north, what happens? They start attracting each other, right? So is the idea clear that electrons can attract each other? The magnetic fields can attract each other. Is that clear?
Yes.
So, Bakyo, clear? Is this clear to everyone?
Yep.
So remember, you've always studied electrons have negative charge, but now you've studied electrons also have a magnetic field, and you can think of them as tiny magnets. And so if one of them has a north pole and a south pole, and the other one also has a north pole and a south pole, and the magnetic fields are opposite to each other, they're going to start attracting each other. So the electron repel electron, the electrostatic force of repulsion, it gets cancelled out. The electrons, they start attracting other electrons. Why? If they have opposite dipoles, opposite magnetic dipoles. You just don't get confused with dipoles. It just means two poles, right? So if they have opposite magnetic dipoles, if one has north, the other one has south. Now the problem over here is that people were still using old terminology. So this is in the old language that is still often used. This is known as the magnetic spin. It's got nothing to do with spin. In chemistry, it's generally referred to as spin because you're still using the old atomic model terminologies, which is why they still call it spin. Otherwise, it's not spin. It's just that they have opposite magnetic fields and they start attracting each other. Now, so the thing is that the dipoles got to be opposite. What will happen if the dipoles are the same? What will happen if this, just a second. So what's going to happen if this was north and this was south? Then the problem would be that it would be impossible to keep the electrons in the same orbital. Like electrostatically, they're repelling each other, negative charge repelling negative charge, and magnetically, they're also repelling each other. So in that case, it would be impossible to keep two electrons together. So whenever you want to keep two electrons together, they always have to have opposite magnetic dipoles, or in chemistry terminology, that's known as opposite magnetic spin. And this spin is referred or represented by two arrows. So there's a box representation. Box representation is that an orbital is represented by a box. And in that box, there's going to be one arrow. Like if you have 2 electrons in that box or in that orbital, there would be one arrow pointing upwards and the other arrow pointing, it's going to be pointing downwards. That just represents that there are 2 electrons. So this represents that's 1 electron, that represents another electron, and they have opposite magnetic spins or magnetic dipoles if they're in the same orbital. Is this clear, this thing?
Yes.
Yes.
So one thing right at the end I'm going to do is, I mean, this electronic configuration over here can also be represented by a box representation, which is going to be like this. That's the first orbital over here. Then you have the 2s, that's another one with 2 electrons. And then you have the 2p, which is 3 orbitals. So this is the 2p, right? So this is 1s2. So that's another way to represent. It's exactly the same thing. So it's 1s2, this one is 2s2, this one is 2p6. Why are there 3 boxes? Because the 2p subshell has 3 orbitals. And all of them are full. So 2 electrons over here. So there would be 2 arrows for those 2 electrons. And the arrows would have opposite direction. The first one is usually up, the second one is downwards. So that's another representation of writing electronic configuration. This is how, and always remember, if they give you a box representation, it's exactly the same thing. Just put in arrows. I mean, those arrows represent electrons. Is this clear?
Yes.
Yeah.
Let's continue with this tomorrow now. We'll try and finish this and we'll try and do past paper questions on this. I'll share the board as well.
Okay, sir.
Okay, then everyone.
Okay.
Sir, when will you share the board once like the notes are complete or?
I'll share it right now on the WhatsApp
Okay.
group. I mean, you can access the board, but I'll make a PDF once it's complete.
Okay.
Just a second. I mean, you can view the board. You can go over there and you can view the board. Okay. Okay, everyone, take care. Allah Hafiz.
All right. Allah Hafiz.